So today we're going to be going over a double differential op-amp question. I struggled a lot whenever I was trying to learn this one, and I couldn't really find anywhere that had this broken down. So at this point in time, we're assuming that you know the basics when it comes to op-amps, right? And the assumptions are correct. No current inputting into the op-amp, and the voltages at the inputs should be the same. So this question asked for us to determine V out for t greater than or equal to 0 at A equals to 2 volts. So because this is a question with two charging components, we need a double differential. Because we need a double differential, we can't just take the derivatives of each of them. We need to insert it into each other so we can really find the answer. From here, we're going to kind of enter our goodie bag of techniques that we've learned. And start off by doing a KCL. Before that though, I'm going to go ahead and label this as VC1 and this as VC2. Perfect. Now, before we even begin, I like to look at the circuit. What do we see here? Well, I see that VC1 goes from this node through the capacitor to ground. So the voltage here should be VC1. So I'm going to go ahead and label this as VC1. Okay? And the second thing I see is that VC2 goes from this node to this node. So if we label this node, let's say Vx, VC2 should equal Vx minus Vout. Okay. Now we're going to go ahead and take our first KCL. I'm going to label it as KCL A. I'm going to take it from right here. So the first part is pretty simple. We've done this 1,000 times at this point. The second part we're going to go through here, right? And because we already labeled this as VC1, there's no need to take the differential from here. We could just go from Vx to VC1 over the R2 capacitor. Now here we will need to take the differential. And if we see from the formula over here, and it should be on your formula sheet, it's going to be the capacitance value times the derivative dVc2 over dt. And that's going to be the current going through that node. So that would be our KCLA. At this point in time, I do not think we can solve it with just this, right? Because we need to find a double differential. And while we can kind of plug this into here, we can't really do anything with it because there's only one differential right here. So we need to take another KCL. We could take one from here, but I don't really see what that gets me at the moment. So we're going to go ahead and take a KCL from right here. And remember, there's no input voltage coming into this operational amplifier. So our KCL is just going to be through this way and this way. We're going to label that as KCLB. We're going to say VC1 minus Vx over R2. And this one, it's going to go through the capacitor, so we need to do the differential, which is C1 dVC1 over dt equals 0. At this point in time, I see that I can go and isolate a term and get something in terms of something else. Because up here we have this auxiliary equation, we're going to want to put something in terms of this one and then be able to plug it somewhere into here to get a double differential. I'm going to choose Vx for that. So at this point in time, it's just a bit of algebra. We're going to break up this fraction here. And we can multiply out our resistance. Making our equation VC1 minus Vx plus C1 times R2 dVC1 dt equals 0. I can go and swap this around and get Vx on this side. And we have officially got our equation in terms of Vx. Okay. Now, we're going to go ahead and find some type of way to get our double differential from here. So what I'm thinking is, we have a differential here, correct? So I'm thinking that we can plug in Vx into this equation and then plug Vc2 into this equation where Vc2 is. Focus on the top section. We basically go and plug in Vx into KCLA over here. We plug in Vx right here and right here. And then we plug in Vc2, which we have up here, into the end. As you can see, plug in Vx here, plug in Vx here, plug in Vc2 here, which then we need to plug in the Vx. So we go and plug in the Vx here. We distribute C2 dt. Apologies, there's a bit of an error. And distribute the C2 term. So we're going to get C2 dVc1 dt plus C2 times C1 times R2. And here is our double differential. That's the part that we've been needing. Now we have our double differential, but we also have V out. And V out's a bit nasty. I don't really want to have to solve for V out. So we're going to go ahead and look back and see if we can find something in terms of V out. I spot that there is a KCL here that we have not done. So I'm going to go ahead and do that now. And as mentioned before, the inputs going into the op amp are the same voltage. We have noted that as VC1. So we can say that the voltage here is VC1. Now we have VC1 minus V out over R3 and VC1 over R4 equals 0. So I spared y'all from all the nasty algebra that we were going to do. As in the previous section, we plugged in Vx, we plugged in Vc2, and then after plugging all of those in, we start crossing out common denominators. And then what we want to do is get our double differential on its own. That's very important here. So we're going to go and multiply out or divide out what is connected to our double differential. And then from there, we go and start factoring terms, simplifying and factoring terms. We want to have one x term, one x prime, and then one x double prime with all the constants on the other side. Now that we have all the constants, we can plug in these numbers. And from there, we're going to need to find our omega naught and our alpha value. From there, we can go and find the dampness, which is then when we need to use this formula sheet. Here we're going to find if it's overdamped, critically damped, or underdamped, and we're going to plug and chug and plug in what values we have and find what values we don't. From here, it's just a matter of plugging in. You should be able to find your answer. Sorry for having to cut the video short. Please like and subscribe.